All right, let's just dive right into this explainer. Today, we're taking a seriously fast-paced journey. We'll start with some absolutely mind-bending physics, and honestly, we're going to end with a profound reality check about the very nature of our universe. You know, we constantly hear about the speed of light, right? But what actually happens when you push past that ultimate boundary? And even crazier, what if everything we've been taught to assume about the speed of light is, well, fundamentally flawed? So buckle up, we're about to totally shatter your perception of reality.
Let's kick things off by dropping right into a physics simulation. Think of it like the digital realm of universe sandbox. We're not chucking a massive asteroid at Earth here, no. We are taking a tiny, completely harmless little 4-gram grain of sand, just a speck. But here's the catch. We're accelerating that tiny grain of sand to a completely impossible speed, literally 100 million times the speed of light. So what actually happens when a microscopic speck of matter smacks into our planet with that kind of kinetic energy?
Well, the results are absolutely catastrophic. I mean, it doesn't just leave a crater. That single tiny grain of sand strikes with such an unfathomable amount of localized force that it drives a literal, instantaneous line of superheated light and energy straight through the entire planet. The Earth's surface temperature immediately spikes to over 300 degrees Celsius. The oceans? Instant vapor. The whole planet is suddenly just engulfed in this glowing cloud of gas. The sheer raw kinetic force of a 4-gram grain of sand literally knocks what is left of Earth completely out of the solar system. No way around it, it's total annihilation.
Okay, so this brings up a rather massive engineering hurdle. I mean, if ultimate speed equals ultimate planet-vaporizing destruction, how do extraterrestrial civilizations, or hey, even future human astronauts, how do they travel through the cosmos without dying? Right? If hitting a literal speck of dust at light speed wipes out a planet, how on Earth, or off it, do you safely fly a spaceship through the galaxy?
This physical reality actually totally dismantles all those pop culture tropes we're used to. You know, the ones UFOs in movies, hovering silently, and then bam, they instantly dart off at 1,000 miles an hour. But physics tells us a different story. Going from 0 to 1,000 miles an hour in one single second creates 50 Gs of force. If you are made of biological molecules, you are instantly turned into a puddle of goo on the back wall of your spaceship. Yuck. The actual physics of reaching interstellar speeds requires patience. You have to approach the speed of light gently, gradually. By maintaining a steady 1g acceleration, which, by the way, handily provides artificial gravity for the crew, you could reach half the speed of light in just about 6 months. And the best part? Your biological body stays perfectly intact.
But look, speed isn't the only problem here, because empty space isn't actually empty. As you approach the speed of light, you inevitably run into what astrophysicists jokingly call space gremlins. Basically, friction from interstellar gas and incredibly deadly micrometeoroids. Remember that grain of sand that destroyed the Earth a minute ago? Well, when your spaceship is moving at even a fraction of the speed of light, simply colliding with interstellar space dust becomes incredibly lethal. So, how exactly do you solve the friction problem? Well, the legendary science fiction master Arthur C. Clarke actually came up with a brilliantly practical solution in his novel, The Songs of Distant Earth. His idea: since you're moving near the speed of light, you just place a massive, replenishable chunk of ice right in front of your spacecraft. As you travel, this giant cosmic bumper just takes all the hits from the micrometeoroids. It's essentially a low-tech force field made of frozen water, and it perfectly absorbs all those devastating impacts of deep space. Pretty genius, right? So the main takeaway here is that, sure, you can engineer your way around the space debris and you can accelerate slowly to save your squishy human body, but you absolutely cannot break the fundamental rule. As astrophysicist Neil deGrasse Tyson so brilliantly puts it, the speed of light is not just a good idea, it's the law. It is the absolute hard cosmic speed limit. But, okay, having established the harsh physical reality of light speed travel, we're about to completely pull the rug out from under you. Because this is where things get truly wild. We are going to pivot right now from physical destruction and space travel straight into a philosophical uncertainty that is basically guaranteed to keep you up at night. What if our entire baseline measurement of the speed of light, literally the very foundation of modern physics, is built on an assumption that we have never ever actually proven? Seriously, let that fact sink in for a second. The speed of light is famously exact, right? 299,792,458 meters per second. But here's the secret. Science has only ever proven the round-trip speed of light. Nobody, and I mean literally nobody in the entire history of human existence, has ever successfully measured the speed of light in a single direction. Every single measurement we have is a two-way measurement. To understand why this is, we've got to look back at Hippolyte Fizeau's famous 1849 experiment. This basically set the gold standard for how we measure this stuff. He's shown a beam of light through the gaps of a rapidly spinning gear, hit a mirror located 8 kilometers away on a hill, and then caught the reflection on its return journey. And honestly, every single experiment since then, whether they're using fiber optics, advanced lasers, you name it, relies on bouncing that light back to the starting point. We measure the total time, divide it by the total distance, and boom, we get our speed.
Now, you might be wondering, well, why not just use 2 synchronized clocks? Put one at the start and one at the finish line, right? Well, because to synchronize those clocks, you have to send a signal between them. And guess what? That signal travels at the speed of light. It's the ultimate catch-22. Albert Einstein actually recognized this massive loophole in his famous 1905 paper. He realized that assuming light travels at the exact same speed in both directions wasn't some proven natural law. Nope. Instead, as he wrote, it was merely a, quote, stipulation that I can make of my own free will. It was, essentially, a scientific gentleman's agreement.
And that agreement is known today as the Einstein synchronization convention. We basically just assume that light travels at the exact same speed in both directions simply because it makes the math neat and easy. We can't synchronize our clocks without knowing the one-way speed of light, and we absolutely cannot measure the one-way speed of light without already having synchronized clocks. So we're just stuck in this endless fundamental loop of logic. Let's look at how this actually plays out in the real world. Imagine we're communicating with an astronaut hanging out on Mars. The total round trip for a radio signal, which remember is just light, takes exactly 20 minutes. Under Einstein's convention, we just divide that neatly right down the middle. We assume the message takes 10 minutes to travel from Earth to Mars, and the reply takes exactly 10 minutes to travel back. It's neat, it's perfectly symmetrical, and honestly, it's comforting. But here is the bizarre, completely mathematically sound alternative. Because we can only measure the round trip, it is entirely possible that light travels at half its known speed in one direction and instantaneously in the other direction. So your message to Mars could take the full 20 minutes to arrive, and the astronaut's reply? It could travel back to Earth instantly, 0 seconds. The total round trip is still exactly 20 minutes. The implication here is absolutely staggering. To us, sitting right here on Earth, scenario A and scenario B look completely 100% identical. The laws of physics do not break if light speed is directional. Every single mathematical equation still holds up, whether light is perfectly symmetrical or if it takes its sweet time going out and then snaps back instantly. It is literally impossible for us to know which reality we actually live in. And that leads us to a pretty stunning realization about how we view our entire universe. Look, we are always told that looking up into the night sky means looking back in time, right? We think we're seeing stars as they were hundreds or thousands of years ago because that's how long we assume the light took to reach us. But if light actually travels instantaneously in our direction, everything changes. The night sky might not be ancient history at all. It could literally be a live broadcast. So, as we wrap up this explainer, I want to leave you with this final mind-bending thought. Everything we know about the cosmos is built on a convention, a choice we made just to keep things simple. But the universe, it doesn't have to be simple. The next time you step outside and look up at the stars, I want you to ask yourself, are you gazing into the deep, distant history of the cosmos, or are you looking at exactly what is happening everywhere right now?